Hello student, welcome to another session of Analog and Digital Electronics. This is Osan Naik from Canara Engineering College. In the last session we have studied about synchronous and asynchronous counter, and we have seen how to design synchronous and asynchronous counter like mod 8, mod 16, etc. In this class we will see how to design the counter of other sequence like mod 6 counter. So first we will see design of synchronous mod 6 counter using JK flip-flops. So the first step here is you have to decide how many number of flip-flops are required. For example, mod 6 in the sense like if I use 2 flip-flops, then it is a 2-bit counter, then it will count 4 state totally from 0, 0, 0, 1, 1, 0 and 1, 1, and this is called as mod 4 counter. It will count from 0 to 3, mod 4 counter. But we want to design mod 6. Suppose if you take 3 flip-flops, then it 2 raised to power 3 gives 8 count, that it will count from 0, 0, 0 to 1, 1, 1, that is 0 to 7. So it counts from 0 to 7, but you want to stop the counting at 5. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. So we want to stop the counting at 5, so that 0 to 5 is nothing but a mod 6 counter. This is called as mod 6 counter. So today we have to design the counter in such a way that after 5 it should return to 0. After 5 it should return to 0. So we will see how this works exactly. So here you see the so we implement this mod 6 counter by using excitation table. So the excitation table for JK flip-flop is this is the present state and this is the next state and the corresponding value of the J and K. So for the more information on this, please refer my last video. So here you can see first you have to write the transition table. So in the transition table you have to write present state and next state. So present state is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. For the present state 0, 0, 0, next state is 0, 0, 1. Similarly, for the state 0, 0, 1, next state is 0, 1, 0. So 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0 and 1, 0, 0, that is 4. The next state is 1, 0, 1 and for 1, 0, 1 the next state 0, 0, 0. So it should count from 0 to 5. After 5 it should cycle back to 0, 0, 0. For other state you have tried just don't care condition x, x, x. Now after writing present state and next state, student, you have to derive the input. What are the input? Since we are using JK flip-flops, JK flip-flops has got 2 input. That's why here for 3-bit counter, when you use 3 flip-flops, totally 6 inputs are there. The 6 inputs are JA, KA, JB, KB, JC and KC. JA, KA, JB, KB, JC, KC. So now let's see first row, that is you will take LSB 0, 0. So QC is 0, present state is 0, next state is 1. So 0 to 1 transition, 0 to 1 transition from the present state to next state. What is the value of J and K? J is 1, K is X. So here you have to write J is 1, K is X. Similarly, QB 0 to 0, present state is 0, next state is 0, 0 to 0 transition is 0x. QA 0 to 0, present state is 0, next state is 0, transition from the excitation table, the value of the input J and K is 0 and X. 0 and X. So like this, student, we have to complete the you have to define all the inputs or we have to derive all the input from the present state and next state. Once the input is ready, then you have to solve this one by using K-map. You have to solve this one JA, you have to map this input in K-map and you have to solve it for the particular expression JA, KA, JB, KB, JC, KC. Let's see that one. Here you can see, so we are using a 3 variable K-map here. The K-map for JA, K-map for KA, K-map for JB, K-map for KB, K-map for JC and KC represent the corresponding value in this one. So you will get the value JA is equal to QB, QC, KA is equal to QC for KB. For KB you will get this value. For for JA you will get this value, for KA you will get this value. Similarly for JB you will get this value, for KB you will get this value, for JC you will get this value and KC you will get this. Once you get this value, then directly draw the circuit diagram. So what is the circuit diagram now? The circuit diagram is, so we are taking 3 flip-flops. So 3 flip-flops are driven by this simultaneously by the clock. Now we will define JA and we will connect JA and KA. What is JA? So go to the previous slide here, just see JA is equal to QB into QC. So I am taking AND gate QB into QC. The output of the AND gate is connected to JA. What is KA? So KA here is nothing but QC. So it is QC. What is JB? JB is Q bar and QC. Q bar and QC. So JB is nothing but take on AND gate. Input to the AND gate is Q bar A and QC, and the output of the AND gate is connected to JB. Similarly, QC is KB and JC and KC. So here JC and KC is 1 and 1. So connect JC and KC to logic 1 or VCC. So this is the diagram for mod 6 counter, which counts from 0 0 0 to 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1. After 1 0 1 it will cycle back to 0 0 0, or it will loop back to 0 0 0. So now students, here you have to see one more thing. So you need to represent the output carefully here. So let me draw the output. This is QA, this is QB and this is QC. So QA, QB and QC, and let me write here, this is QA, this is QB and this is QC, and our output is this is QC, QB and QA. This is the output representation in terms of truth table. So in this way we can design any type of counter. So we will see the next one by using either D flip-flop or a T flip-flop. So students, will see now the mod 6 counter design using D flip-flop. As I said earlier, so you have to define or derive the input by using transition table. In the transition table you have to define the present state and the next state. For the D flip-flop here, for D flip-flop, like we are not going to, for the counter design, mod 6 counter design using D flip-flops, we are not going to define separately data input. Here we are taking directly present state and next state, because we know whatever data at input that will be moved to the output in case of D flip-flop during the either positive edge or negative edge. So we are directly taking the next state and we are mapping that mapping these values in the K map, and we will derive the equation here. So present state is like 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1. But the next state is 0 0 for 0 0 0. The next state is 0 0 1. Similarly 0 1 0. But you have to remember here When the count reaches 5, 1, 0, 1, next state is 0, 0, 0. After that, that means it will loop back to 0, 0, 0. After that, for the next two count, you will take the output as don't care condition. Now let's solve this one by using K-map. When you solve this one using the K-map, you will get the expression. This is the expression what you get here for DA, DB and DC. Directly we will map this one. Here we are not going to define separate this one. Directly we are going to map these values in the K-map, and you will get this expression. Once you get this expression, it's very similar to draw the circuit diagram as we have seen earlier. This is the circuit diagram where we are using 3 flip-flops here. Students, we are using 3 flip-flops. You see, this one is DA, 3 flip-flops, DA, DB and DC. So 3 flip-flops are connected by simultaneously driven by single clock. Other than that, what is DA? DA is nothing but DA is nothing but this is nothing but we need to use 2 AND gates and 1 OR gate, and we need to draw the circuit diagram for this expression here. So here you can see here the circuit diagram by using 2 AND gate and OR gate. Similarly for DB and DC. So with this way you can design a D flip-flop mod 6 counter, mod 6 counter by using D flip-flop. So in the next session you will see how to design mod 6 counter by using D flip-flop.